is to design the shear reinforcement. Step 5 is design the shear reinforcement. For cantilever beam, we have the shear force formula, that is Vu is equal to WL. So substitute all the value. After simplifying, we'll get our shear force value as 261.52 kN. So after this, we'll go for the calculation of nominal shear stress, that is denoted as tau v. So for this formula, we need to refer the page number 72 of IS 456 2000 clause 40.1. We will see what they have said. So this is the page number 72 of clause 40.1, nominal shear stress. The nominal shear stress in beams of uniform depth shall be obtained by the following equation, that is tau v is equal to Vu divided by B into D. So by using this formula, we will calculate the nominal shear stress. So same formula I have written here. So substitute all the value. After simplifying, we will get our tau v value as 1.97 Newton per mm square is our nominal shear stress. So after that, we will go for the calculation of percentage of tension steel reinforcement. So to calculate the tensile steel reinforcement, we need to refer the page number 37 of IS 456 2000, table number 19. So this is the table number 19 of IS 456. So by using this formula, 100 AST divided by BD, by using this formula, we will calculate the percentage of tensile steel reinforcement. So by using this formula, we will calculate the PT value. So 100 into our AST provided is 2945.22 divided by B is 230 into D is 575. So after simplifying, we will get our PT value as 2.22%. So now what we need to do is we will go for the calculation of tau C. So by using value of PT and our FCK value, we will calculate the tau C value. So to calculate the tau C, again we need to refer the table number 19 of IS 456, page number 73, to find out the tau C value. This is the page number 73 of IS 456, table number 19, design shear strength of concrete, that is nothing but tau C, Newton per mm square. So by using this table, we will calculate the tau C value. So this column as the value of our PT value, percentage of tension steel reinforcement. So why we need to calculate the PT is because this column has the value of percentage of tension steel reinforcement. To find out the tau C value, we need to calculate the PT value. So by using PT value and our grade of concrete, will calculate the tau C value. So our PT value we have got is how much? We have got is 2.22 we have got. So 2.22 means where it comes in between 2.00 and 2.25. It comes in between these two. So for 2.00 we have the M20 concrete value, that is the corresponding value is 0.79 for 2, and for 2.25 we have the concrete value 0.81. So by using this value and by doing the interpolation, we will calculate the tau C value. So I will show how to do the interpolation. So for PT value 2.00 we have the tau C value 0.79. For 2.25 we have the value 0.81. So I will show interpolation method, that is tau C. So we will take the least value, that is 0.79. Why we take the least value means this value goes on increasing. So I am taking the least value and plus I am adding it because this value goes on increasing, that's why I am adding. So least value plus into the greater value minus least value, that is 0.81 minus 0.79. divided by again the greater value minus least value, that is 2.25 minus 2.00 into the value which you want to find out, that is 2.22. 2.22 minus the least value 2.00. So 2.00, substitute all the value. Auto simplifying will get our tau c value as 0.80 Newton per mm square. This is how we do the interpolation. I hope you understood. So next step is to comparison of tau b value and tau c value. So now comparison of tau b and tau c value. So our tau b value which we have got is 1.97 Newton per mm square, and our tau c value is just now we have calculated. Tau c is equal to 0.80 Newton per mm square. So compare this, which one is least. So our tau c value is least and our tau b value is greater than this. So when our tau c value is greater than tau b value is greater than tau c, so we need to do the shear reinforcement is needed. So we need to calculate the shear reinforcement when our tau v exceeds tau c. So for that again we'll go to page number 72 of IS 456 2000 clause 40.4. So what they have said, to design of shear reinforcement when tau v exceeds tau c, that is nothing but when our tau v is greater than tau c, so shear reinforcement shall be provided in any of the following forms, that may be in the form of vertical stirrups or bend up bars along the stirrups or inclined stirrups. So what they have mentioned, when our tau v value is greater than tau c, we need to provide the shear reinforcement in the form of these three. It may be vertical stirrups or bend up bars or inclined bars. So for vertical stirrups, they have given the formula VUS is equal to 0.87 Fy ASV D divided by SV. By using this formula, we will calculate. So they have said one more here. For shear reinforcement shall be provided to carry a shear equal to Vu is equal to tau c Vd. The strength of shear reinforcement, that is VUS, shall be calculated as below. So by using this formula we will calculate the VUS, and by using this formula Vu is equal to tau c Vd, we will calculate the shear carried by concrete. We will show one by one. So as per clause 40.4 page number 72 we have just seen. So now to find out the shear carried by concrete by using VUS is equal to tau v into Bd. So substitute all the value and simplify this, will get 105.8 kilonewton. So after this we need to calculate the shear carried by stirrups. So that is denoted as VUS is equal to VU minus VUC, shear carried by concrete. So substitute all the value. After simplifying we'll get our VUS value as 155.72 kilonewton. So this is how we calculate the shear carried by concrete as well as shear carried by stirrups. So now what we have to do is we'll go for the design of spacing of stirrups. So now spacing of stirrup should be calculated. So for that again refer page number 72. I have shown by using this formula we'll calculate the spacing of stirrups. For that I moved this to here. SV is equal to 0.87 Fy ASV D divided by VUS. So to find out the SV, what is unknown here, we have the value of Fy and D and VUS we have calculated. So here ASV is unknown. So now we'll go for the calculation of ASV. So for calculation of ASV again we need to assume diameter. So I am assuming two legged vertical stirrups of 8 mm pi bars to calculate the ASV. So ASV is equal to 2 into pi by 4 into 8 square, that is diameter. So after simplifying, we'll get our ASV as 100.53 mm square. So substitute this value in equation number this. In equation this. So 0.87 Fi value is 4 and 5 into ASV is we are calculated, that is 100.53, and our D value is 575. So our BUS value is 155.72 into 10 to the power of 3. After simplifying, we'll get our SP value as 134.02 mm. So call it as equation number 1. So now, refer page number 47 and 48. So there is one more criteria. We'll see what it says. This is the page number 47. So maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 d for vertical stirrups. So our spacing of stirrups should not be greater than 0.75 d. They are mentioned. And D for inclined stirrups at 45-degree angle, where D is the effective depth of the section. This is the one criteria. We need to apply this. There is one more rule. In no case shall be spacing exceed 300 mm. So our spacing of stirrups should not be greater than 300 mm. So these rules also we have to apply. So I will show step by step. We'll see one by one. So our SV should not be greater than 0.75 D. They have mentioned. So our D value is 575. Substitute all the value. After simplifying, we'll get our SV value as 431.25 mm. So call it as equation number 2. So our third condition is our SV should not be greater than 300 mm. So that is nothing but our SV is equal to 300 mm. So call it as equation number 3. So now our spacing of stirrups should be least of these three. So which is least? The first one is 134.02 mm, and the second one is 431.25 mm, and the third one is 300 mm. So which is least? So the 134.02 is least. So I am making it into 125 mm. So it is least. I am taking our SP value as 125 mm. 125 mm. So I will take this. So our SV value should be least of the above three equations. So 125 mm is the least. So I am taking SV value as 125 mm. So provide two-legged vertical stirrups of 8 mm pi bars at 125 mm center to center distance. So whenever you are calculating this, you will take the value which is least you should consider, and sometimes you will get the value more than 300 mm, that is 350, 400, 450. That time you need to provide the least value, that is 300 mm, minimum 300 mm. So sometimes you will get less than 300 mm, that is like 125, 150, 250. That time you will provide the least value whatever you got. So this is we'll calculate the spacing of stirrups. So after this we'll go for the calculation of development length. So in cantilever beam we have to provide the development length. For that we need to refer as per clause 26.21 page number 42 what it says. We'll go to page number 42. So this is a page number 42. Development length of bars. The development length LD is given by LD is equal to pi into rho s divided by 4 into tau BD. So our pi is the nominal diameter of the bar and rho s is a truss in bars, rho s, and tau BD design bond truss. Tau BD is design bond truss. What they have mentioned here is for deformed bars, conforming to IS 1786, these values shall be increased by 60%. So what they have mentioned for different bars, that is HYST bars. So what are the values we are going to use as design bond trace, that is tau BD. So the value is again increased by 60%. So like I will show for example. So grade of concrete is 20. So for that our tau BD value is 1.2. This value is again going to increase by 60%. So we'll see. So our 1.2 value is again increased by 60%. So this formula is given on page number 42. So pi is the diameter of bar. You can take any value. So rho s is stress in bars. So that is rho s is nothing but 0.87 Fy. So for our tau BD value is for M20 I have shown, that is our tau BC bond stress value is 1.2, and this value is again going to increase by 60%. So as they have mentioned in our code book. So for defined bars, the value of 1.2 or tau BD value is again increased by 60%. 60% nothing but 1.2 into 1.6. So substitute this value in this. So our LD is equal to 0.87 into Fy is 4 and 5. So I am taking diameter as 25. So 4 into 1.2 into 1.6. So after simplifying we will get our LD value as 1175.29 mm. So I am making it approximate value, that is 1200 mm. So this is how we calculate the development length. I hope you all are understood. So now we'll go for the drawing of reinforcement details of cantilever beam. So I will show where it comes in our beam. So this is the longitudinal section of our cantilever beam. We'll see. So in our cantilever beam, the tension reinforcement comes on top and compression reinforcement comes bottom. So here 6 numbers of 25 mm pi bars at top side, that is tension reinforcement, and this is the compression reinforcement. 4 numbers of 25 mm pi bars. The compression reinforcement comes bottom and tension reinforcement comes on the top because it is cantilever beam. So these are the stirrups which we have provided. 2-legged vertical stirrups of 8 mm pi bars at 125 mm center to center. The overall depth of the beam is 625 mm. So our effective span of the beam, that is capital L is equal to, they have given in our problem, that is 4 meters, nothing but 4000 mm. And these are the supporting bars. The supporting bars, why we have provided this is, so when the required number of bars exceeds the capacity of a single layer at that time, so the bars are arranged in multiple layers to satisfy both the total area requirement. So that's why I have provided one more layer here. So you can see here. So in cross section diagram I will show. So this is the cross section diagram. So as shown in cross section beam, so 3 bars are fit in the top, that is first layer. 3 numbers of 25 mm pi bars at first layer, and again 3 bars are, that is 3 numbers of 25 mm pi bars at second layer. They are fit below the first layer. So this is the supporting anchor bar, and these are the stirrups which we have provided, and these are the 4 numbers of 25 mm pi bars compression reinforcement, and our 230 mm is our width of the beam. So why we have provided 3 bars in first layer and another 3 bars in second layer is, the when provision of 3 bars in the first layer and 3 bars in the second layer is due to required total area of steel for tension reinforcement which cannot fit into the single layer, so that we have to provide another 3% second layer. So this is how the arrangement of the bars. So, and this is our development length, so which we have got is 1200 mm. So I have extended, so the mean tension reinforcement extended into the column to the length of 500 mm, and it bent at 90 degree, that is here extended up to 200 mm. After that it extended up to 500 mm. So our overall depth of the beam is 625 mm. So we cannot provide directly the our LD length, that is 1200 mm. So we need to extend it, and after that bend at 90 degree and again extend at 500 mm. So our total length is 1200 mm. This is our development length. So this is the reinforcement drawing of our cantilever beam diagram. I hope you guys are I hope you all are understood. So if you like the video, press the like button, share it and subscribe for the more videos. Thank you for watching.